Now, we said that if velocity is changing displacement over time, then angular velocity will what? Angular displacement over time. Good. So from here, angular displacement what?
Angular velocity
Times
times
time.
time.
Does this make sense?
Yes, sir.
So if this makes sense, then we can introduce it into the equation. Recall that theta is equal to omega t. Therefore, we have y equal to a sine omega t minus phi. You also remember that phi is kx, and what is k? 2 pi over lambda. So meaning that phi is what? 2 pi x over lambda. Do you remember this thing? Alright. So y is equal to a sine omega t minus pi x over lambda. God bless you. Now, recall also that, do you remember that omega is 2 pi f? Do you remember this? Let me show you how. Remember that we said omega is theta over t, right? If the total angle that it completes is the entire circle, that's 360 degrees, right? Which is equal to 2 pi. You get that, right? Time taken to complete a circle is called what? Period. Right? So it's not just time, now it's period. And f is what? 1 over t. So this is 2 pi times 1 over t, which is f. So omega is equal to 2 pi over f. Does it make sense? I know you were not even organic, right? But does this make sense to you from what I did, right? We said that angular velocity is displacement over time. So yeah, which means that if the thing covered the entire circle, then you have 2 pi. Then the time taken to complete the entire cycle is called period. It's a special time. And frequency is the inverse of period. We've derived that before. So 2 pi times 1 over t therefore becomes 2 pi f. So if that's the case, then here can become y equal to a sine 2 pi f t minus 2 pi x over lambda. Is it making sense? Is similarly confused? Are you following? You know why I like you to know how to derive this thing? Eh? Here's the reason. Students often forget the formula. I don't want you to just cram it. You know how the derivation goes. Once you use it, once you get home, try the derivation yourself over and again, over and again. Is it clear? Alright. From here, you remember that V is equal to F lambda. Do you remember? Meaning that F V over lambda, right? So we can substitute into that equation. We have made many equations now. Equation 1, equation 2, equation 3. So here becomes y equal to a sine 2 pi v over lambda t minus 2 pi x over lambda. Okay, that's equation 4. Looking at this also, you can see that 2 pi over lambda is common. Do you notice? So since it's common, we say y is equal to a sine of 2 pi over lambda is common between when we use a vt minus. So this is the last equation we probably need. Is it clear? Is it clear? Alright, quickly drop it. I know it. So this one says, so we have to solve these four questions. All right, the last one I picked is in question 48. It says, given the progressive wave equation, y equal to 5 sine 2000 pi t minus 0.4x, calculate the wavelength. Now, it says you calculate what? The wavelength. Which of these forms of the equation does this look like? Which form? In my opinion, seeing that pi is inside here, then it cannot look like this. It either look like this or like this. Okay? So I'm going to go with this. Exactly. So I'll now compare. You are not listening. Y equal to a sine of 2 pi ft minus 2 pi x over lambda. From here, just compare. Y is y, right? 5 sine, a sine. So a will be what? 5 meters. I mean, given that we are giving in meters. Do you understand now? Just compare. 5 is A, so A is 5. If we have to find amplitude, we'll just say it's 5. Alright, but we're not have to find amplitude. We now compare these two sides. Look at this side and this side. They look very much alike, right? Compare these two sides. What are we looking for? Wavelength, right? Yeah. So which two sides should we compare? Yeah. So 0.4x is equal to 2 pi x over lambda. Now listen. The reason why I wrote this ahead is because they are negative, negative. So negative, positive. If I put the negative, negative, it cancel out. Is that clear? Alright, so from here, this cancels this. Make sense? As if I divide both sides by x will cancel here, x will cancel out here. Right? So we have 0.4 is equal to 2 pi over lambda. From here, I can divide both sides by 2. If I use 2 to divide here, that's times 1 over 2 here, times 1 over 2. Here 1, here 1. 2 here 1, 2 here 0.2. So pi over lambda is equal to 0.2. So to get pi here, I can cross multiply, right? If I cross multiply, I have pi is equal to 0.2 lambda. So lambda is equal to divide by 0.2. So lambda is equal to pi over 0.2. Is in the option? Check question 48. No. No. What's in the option? If it's not a fraction, we'll change it to decimal. 12 point what? 12.4. Look at this. What's 0.2? 1 over 5, right? So lambda becomes. Is it wavelength I have to find? Let me see. Two pi x over lambda here. Yes. No. Let's do it again. If we compare this side and this side, we compare this side and this side. 2000. This is where lambda is. Let's find the value of frequency. Let's find the value of frequency first. This will be 2000 pi t is equal to 2 pi ft. Pi cancels pi, right? T cancels t. 2 here 1, 2 here 1000. So f is equal to 1000. And v is equal to f lambda. So that lambda is equal to v over f. But we don't have v here, right? Okay, so no, we cannot use the last formula. Do you know why? Because here pi is factored out, and pi is not factored out here. Pi is part of the equation. So if it's inside the bracket, we use an equation that has pi inside the bracket. Do you understand now? Let's equate it again. 0.4x is equal to 2 pi x over lambda. We divide both sides by 2 here 1, here 0.2. X cancels x. Then lambda will be equal to pi over 0.2. And lambda is equal to this 1 over 5, that will be 5 pi. Do take pi to be 22 over 7 and use your calculator. Do 5 times 3.142. Do 5 times 3.142. 15.7. Isn't the option? Isn't the option? It's correct, but well, it's a jam question. But most cases, they usually leave pi in the answer. You see other questions like that. But do you understand what I did? So this was needless. This was needless. What we did is correct. Is that correct? Do you understand what I did? I simply compared. I have this equation. Why did I pick this? Because I saw the form of my equation. So I knew that this one that would look like it. So I compared this side and this side. So since it's the same equation, I will equate this side to this side. This side must be the same. This side and this side must be the same. This side and this side must be the same. Y is Y. Is it making sense? So I now equated this and this. By equating, you do your own maths. Or for speed's sake, just do 2 takes care of 2, 2 takes care of this, gives you 0.2. Is it clear? So 0.2 equal to x takes care of x equal. So you make y lambda solve formula, you get this. So if you do 22 over 7 divided by 0.2, this is what you get. 15 point whatever they said. Is it clear? Alright. Let's do the second one. What does the second one say we should find? Let me see where I got it. Question. So I will do the second one. Which one should I do between y and 2 and 3? I should do 3. You do 2. I'm looking for it. Question. This 3, right? This 3, right? Yes. Is from question. Yes, question 33. So let me do that. Question 33 says, the equation of a wave traveling along a positive x direction is given by this. Determine the angular frequency. What's the angular frequency? Omega. Is that clear? Omega. And it's also called angular frequency. Yes. So, so which one should we use now? You remember there was one of our equations that we said a sine omega t minus 2 pi x over lambda. So this is the equation we use. So we equate this side to this side. Is it clear? So from here, what's the answer? You need to solve. Wait, don't say the answer. What's the answer from here? You are equating this side to the other side. This equation to that equation. So what's your omega? Eh? 500. What's 500? 500 now. 500. Omega t. This side is equal to this whole side here. What's our amplitude there? This, right? Sine. This is equal to this. 500 t. T cut t. Omega is 500. Exactly. That's option B. Option one option that says 5 times 10 to the power 2. Do you see that? That's option C. 5.0 times 10 to the power 2. Don't let those things confuse you. 5.00 take order. 5.00 times 10 to the power 2 rats per second. Is it clear? Who is confused? Nobody. Alright. This one, what does it say we should find? This number. 0.3 something. Alright, this is in question 27. Question 27. Yes, question 27. So it says you find what? Is given by that. Find the maximum displacement. What's that? Maximum displacement for equilibrium position is called what? Maximum displacement from equilibrium position is what? Maximum upward or downward displacement. What are you looking for there? Maximum upward or downward displacement. Maximum upward or downward displacement. What's it called? Of a wave. The maximum upward or downward displacement of a wave is what? Is the amplitude of the wave. Thank you. The maximum upward or downward displacement. That's amplitude now. So what's the amplitude of that thing? What's the answer? Do you need to solve? No. It's funny, right? That's why I'm laughing. Like you just see that question like he did not it. Just look at it. Amplitude is this. Is it clear? But from here, what if I just wanted you to solve. I say find wavelength for me. What would the wavelength be? See this now, see this. Let's compare it with this side. I like to compare it with this side. So if I compare it to this side, wavelength will be where? Is with the guy with X, right? So it will be with this guy. So it will be 0.5x will be equal to what? Minus 2 pi x. Is that correct? Alright. So from here, x takes care of x. That size by 2. 2 in 0.5, that's 4. That's 0. That's 1 over 0.25. 0.25. 0.25 is equal to pi over lambda. So lambda is equal to pi over 0.24. That's 4 pi. 4 pi. That's 12 point something, right? No. 4 pi. Is it clear? Is it hard? Alright, try the first one. What is it? The first one says you find velocity. Let me teach you what you must first do here. See. Let's use this x to multiply through. So open the bracket. Exactly. So x will appear here and here, but you must be smart. C is here. So if you use this, for example, it means that you equate this one with this one. Does it make sense? Then x squared will be in this side. You equate it to this side. Is it clear? Quickly try your thing. By the way, you can also use this to open the brackets to make sure that it looks perfectly like this. Remember here, pi is collected outside. Pi has not been collected outside here. I mean, except you want to use this side. That's another thing. Use this. You can use this as well. Is it making sense? Use anyone you prefer. Quickly. To find the velocity. You are looking for velocity. Let's do it together. Watch. The first thing you're supposed to do here is y will be equal to 0.005 sine pi. Let's leave that on outside. Open bracket 0.5x squared minus 200xt. Let me ask you, what's the amplitude of this thing? What's the maximum downward displacement of this thing? Downward displacement. That's the amplitude now. That will be 0.005. Is it right? So from here, we compare it with, which part of the equation is best to compare it with? This last one. This one. This one. I won't use this. Why? Because pi is inside here. And here, pi is outside. So I prefer this. Do you understand? I prefer to use that. Or I can even use this in a special form. You understand? This one now, I'll just collect 2 pi out. It becomes y equal to a sine 2 pi over ft minus x over lambda. It still works. But let's use that last one since it's what you used. So vt will be on this side, on this side, and x will be on this side. That last one cannot earn us much. Can't give us much. So you know what I'll do? I'll put this guy. I'll distribute it so that y becomes a sine of 2 pi into bracket vt over lambda minus x over lambda. I mean, it doesn't even change much. But you know what I do? I just return this pi to there. Is it clear? Raima doesn't look convinced. See, if you do 2 pi over lambda, see, vt minus x, this doesn't give us a lot of information. Why, for example? Where we find t will be equal to this one, right? That makes sense, right? So we have minus 200xt is equal to vt. Here, t cancels t, and v will go to minus 200x. Okay? But we need a value for, so we now say here, minus x is equal to this side, right? 0.5x squared. X takes care of x, right? So we have minus 1 is equal to, minus 1 is here, right? 0.5x. Divided by 0.5. So x equal to minus 2. 0.5 is 1 over 2. It goes up, 2 goes up, becomes. Make sense? Yes. So from here, x is minus 2. So it comes here. V becomes minus 200 times minus. Make sense? Minus. Minus and minus plus. And whatever method you use, should we use another method? Let's use another method. Is it clear? Let me show you what I said if you use there. This one. Should I see? You used and you got 400. Good. Whichever method you use, you get the same answer. Y equal to a sine 2 pi into bracket ft minus x over lambda. Please, when you get home, derive this equation, derive as many as possible. Do you understand? It will give you, good understanding. Now, I know that x is here. So this one that x is squared here will be equal to this. Why am I not using this? Because t is here and t is not here. Is it making sense? So if I equate this to this, I'll have minus 200 xt is equal to ft. This xt of this, f equals to minus 200 x. I keep this. Then minus x over lambda is the same as 0.5 x squared. From here, x takes care of one of the x's, and I have 1 over lambda another 0.5 x. And now you see, there's a problem here. I mean, there is no problem really, there is no problem. See what I'll do. Lambda will become, if I take this guy up, this guy will come down. Do you believe? Okay, cross multiply. Cross multiply minus 1 is equal to 0.5x lambda. The other side is 0.5x plus 0.5x. This takes care of this. So lambda is equal to minus 1 over 0.5x. Now, what do? And v is equal to f lambda. F is this, minus 200x times lambda is this, minus 1 over 0.5x. X cancel x. 0.5, 400. This is whatever method you use, you get the same answer. That's what you did. Do you understand now? Alright, good. So now, when you get home, solve other questions on this particular one. Is it clear? Alright, let's attempt questions now. Now, question 1, share that. Question 1 says, let's be quick, please. I'll be reading the question and you tell me. Question 1 says, question 1 says, a string is sustaining a stationary wave. Stationary wave. When is it a stationary wave? A, when the frequency of the wave is not proportional to the wavelength of the wave. That does not even make sense. Question 1. B, the amplitude of the vibration is always 0. No, that's not when it's stationary. When the amplitude is 0, it means there is no wave at all. C, 2 equal waves are traveling in opposite directions. That's standing wave. That's stationary. That's the answer. C. The next one, which of the following types of waves cannot... Do we all get that? Yes. Number 2, which of the following waves cannot travel through a vacuum? Vacuum means they cannot travel through a vacuum. It means it requires material medium. Which kind of wave require material medium? What do we call them? Based on medium of propagation, we have 2 types of waves. Mechanical and electromagnetic. So that's mechanical wave. So which one here is a mechanical wave? Is it clear? That cannot travel through a vacuum. A, sound wave. B, light waves. C, infrared. D, X-ray. D, radio wave. Or E, radio wave. What's the answer? Do you remember this? No. RMIXVUXG. Do you remember it? What are these guys? What are red? No, the other side is like, so that one. Roy beef, that's radio, that's visible light. Roy beef, that's visible light. So what are these called? Which spectrum is this? Electromagnetic waves. And we have two types of wave based on whether they require material medium or not. We have mechanical waves and electromagnetic waves. Mechanical waves are the ones that require material medium, hence they cannot travel through vacuum. But electromagnetic waves, they don't require material medium. Is it clear? Electromagnetic waves, don't, you are still saying nonsense. Electromagnetic waves don't require material medium, hence they can travel through vacuum. So this guy can travel through vacuum. This guy, I mean, radio wave, microwave, infrared wave, all visible light, ultraviolet, X-ray, and gamma ray. So which one? Did I tell you that if you vacuumize the environment, it will not travel? Sound wave. If you say, oh, they are not carried. Big edge. If the wavelength of a wave traveling with a velocity 360 meter per second squared is 60 meter, the period of the wave is what? Now it's very simple. You don't even need to touch a book. But in case, for those that might have forgotten, V equal to what? F lambda. Or V equal to lambda over F is 1 over T. So 1 over T times this is lambda over T. Is it clear? So here we have the speed, we have the period. What are we looking for? Period, right? So period will go to what? Lambda over V. What's lambda? 60 over 360. 1 over 6, 0 point what? 17 seconds, I think. 1 over 6 is 0.17. Right. Is it hard or simple? Simple. Is it simple? When master do it with us, right? Is it simple? When you do it with us. Number 4. For the wave motion represented in the figure below. In the figure, the wavelength is given by what? What's the wavelength there? Is it Q, S, P, T? Number 4. What's the wavelength there? Go and share. Go and sit with someone. Sit with Adam. Wavelength, a cycle. Which one is a complete cycle there? God bless you. Yes, now, yes. Adam. No, it's not D. By throw this mark on. It's not D. It's J. It's S now. When you have a wave like this, I told you 3 different definitions of wavelength. Difference between 2 successive crests and 2 successive troughs. Is it clear? The next one, number 5. Any line or section through an advancing wave in which all particles are in phase is called the dash. No, that one, there is a mistake there. There's a typo. Take your chair and sit with Adam. Any line or section through an advancing wave in which all the particles are in the same phase is called, you wrote light waves there, radio waves, sound waves, surface waves on water, X-rays. No, there is a typo there. The answer to that is wavefront. The answer to that is what? Wavefront. But to be on the safe side, if you have a question like this, the answer you should pick is D, surface wave on water. Because see, you know it's water wave that spreads like this, right? If I make a drop here to spread out like this. So what this wave is saying is that If I draw a line that shows all this part and this part they are in phase, right? All these parts they are in phase. So this is a wavefront. It's called a what? But the reason why I said you should choose DD is because we study wavefront using water. Exactly. Alright, the next one. The following types of waves are all transverse except this is what they did there. The option in question 5 is supposed to be for question 6. You see that is a very silly option that they put there. It's a typo. Do you understand what I'm saying? Raise the temperature of unit mass of substance. Does that make sense? Is that wave? And so that option for question 5, put it in question 6 now and tell me the answer. The following waves are transverse waves except which one is not transverse? Sound waves, God bless you. Sound wave is longitudinal. Now, longitudinal, as you say it, to be going forward, right? Longitudinal. Right. The next one, number 7, the wave motion shown has frequency of what? Now that one, this thing is given there. Now, it's not even clear in the way they drew it. But look at what they are trying to show you. See, this place that they put 0.01 is the amplitude. Is it correct? Then this place is 0.1, this place is 0.2. So what are you have to find here? Frequency. Who can find it for us? Frequency is 1 over period, right? What's the period of that wave? The period. Period is time for one circle, which is what? 0.2. That's one. The terms are there, like give you Japan. You know these things. It's just you are not opening your eyes. 0.2. So 1 over 0.2 is what? 4, right? Is it 4 or 5? 5 rather. 0.2 is 1 over 5. That's 5. Is it clear? Who is confused? Are you confused? She understands what we did. We did 1 over 0. Baba, look at your book. Okay, if you are vexed, tell us the next answer. The combination of sound waves with different frequencies is what? A, interference. No, I didn't tell you this one. A, interference. B, diffraction. But I want you to try. C, superposition. D, forced vibration. What's the answer? What is superposition? Now, you see, I didn't tell you about forced vibration. Forced vibration does not have anything to do with frequency. No, it has something to do with frequency. Forced vibration is this. Let me show you the different type of vibration. We have free vibration. This is free vibration because I allow the molecules of the gas to vibrate by itself and then it sends the sound. Dampened vibration is I touch it, maybe I hold it, and then you see the sound will be cooler, right? Then forced vibration is I cause the entire particle to maybe I hit it so that it shatters. Do you understand? Alright. Now, so it doesn't have anything to do with that one. This question. Do you understand now? The resonance is this. I vibrate one body. If I set this body in motion, and that motion causes this second body to vibrate. For example, if airplane is passing, you notice you'll be feeling. Now this is if I put a bad bass instrument speaker here, I'm playing this thing. The wall is vibrating, right? That's resonance. Exactly. The vibration of the body, when one body vibrates at its natural frequency and is passing on that vibration to another body, is called what? Resonance. Does it have anything to do with that? No. So the answer is superposition. Is it clear? Superposition. For interference to occur, I told you there must be what? Equal frequency. And equal frequency. Is that clear? Number 9. We will wait for you. Ripples on water are similar to light waves in that they both what? Ripples. What's the relationship between light wave and water wave? Who can tell me? Relationship. What is the relationship between water wave and light wave? I say, what's the relationship? What makes them equal? What brings them to you know? What relates them? What is similar? What do they have in common? Yes. What do they have in common? Light wave is transverse because all electromagnetic waves are transverse. Let me ask you a sincere question. How many of you have read the note I gave you? The note I gave you on waves. You have not read it. You say you are scoring anything. And read the note. Is that clear? Read the note I give you. Water wave is transverse. Why? Because the direction of propagation is different from, is perpendicular to the vibration that produces it. Direction of propagation will be like this, but the motion producing it is up and down. That's transverse. Light wave too is what? Electric field of the earth and magnetic field of the earth at 90 degrees to each other. So that's the relationship between them. Exactly. Well, let me use common sense to bring in the relationship here. It says they are similar. How? They both, is it that they have the same wavelength? Eh? Do they have the same wavelength? You can't even say that they have the same. It doesn't even make sense. Do you understand? Are longitudinal? Are they both longitudinal? That one is very wrong because they are both transverse, right? Cannot be reflected. Can they not be reflected? Light can be reflected. Water too can be reflected. You see that if it hits the side of the DC to come back again as ripple, right? To send back the ripple now. Yeah. Good. So that it can be reflected. Travel at the same speed. Do they travel at the same speed? How can water will travel at the speed of light? Now the next one can be refracted and diffracted. Water wave, light wave can be refracted. Can water wave be refracted? Now actually, look at, they have same wavelength. That is out of it. Look at, they are longitudinal. Not correct at all. Cannot be reflected. It's not correct also. Travel at the same speed. Rubbish. So now, if you are not sure of E, we are not sure of E because we don't know if water can be reflected. So E is the best bet. I don't know if you understand what I just did. We are not sure if water wave can be refracted. Of course, right? But every other option is wrong. I don't know if you understand. So E must be the correct answer. Is it clear? If you pick any other answer there is wrong. Or which other answer is correct there? Do you agree with me? Yes. All right. You don't say why now. You don't say it's because the other side. It's you now. It's not you, my Simon. All right, the next one. Longitudinal waves do not exhibit what? Longitudinal wave. They do not exhibit what? A, refraction, B. Reflection. C. Diffraction. E. Polarization. E. Rarefaction. For example, now let's do elimination method again. Longitudinal wave. Example of longitudinal wave. Sound wave, right? Now, can sound wave be reflected? Yes, that is echo now. Yes, that's echo. Rarefaction. We saw that under sound wave, right? Polarization. No, the answer is polarization. You only polarize transverse wave because transverse wave is the one that has two angles. Okay, one is traveling like this, the other one is traveling in and out of the board. Exactly. So it's this one that can be polarized. But for a longitudinal wave that is traveling in just one direction, it doesn't need polarization. I don't know if you understand. Is it clear? All right. The next one. Number 11. Radio waves has velocity of 3 times 10 to the power 8. A radio station sends out a broadcast on frequency of that. The wavelength is what? Just combine V equal to F lambda, right? Everybody can solve that, right?
Yes, sir.
Who cannot solve it? Don't lie, don't lie, don't lie. You remember this equation now? V equal to F lambda. You have been given V there, right? It's 3 times that speed of light, right? And the frequency is given also 800 kilohertz. That is 1,000. Oh. Don't forget that too. So you are looking for lambda. Lambda is equal to what? V over F. What is V? This over this. Is it clear? Let's go. For you, I can take anything, exactly. Even a bullet. Oh, what is the hell? Like you have someone to come and shoot me to confirm that. Don't worry, okay? Let's continue. This one now. A wave of frequency 10 Hz form a stationary pattern of in a medium where the velocity is that. The distance between adjacent nodes is this. Now, I have not taught you wave through a pipe. So we'll skip this question. When we treat stationary wave, we'll deal with it. Is that clear? Alright. The rest, I guess you should be able to do it. Is that clear? Look at question 16. Question 16. There are two waveforms there. Waveform X and waveform Y, right? How many cycles is in waveform X? Check now. 1, God bless you. How many cycles is in waveform Y? Good. It says if the diagram above are two waveforms, if the frequency is 30 Hz, what's the frequency of Y? Okay, that's if the frequency of X is 30 Hz. What will be the frequency of Y? Who cannot do it? You simply say that one cycle. Do you understand now? That one cycle is 30 Hz. Therefore, 2.5 cycles. Do you understand now? And alright. So I guess we are done. Now let's go to reflection of light. Right. Let's start. Reflection of light. Yes. So in order to understand reflection, we have to first treat what light is. Reflection, right? Reflection. This is the change in direction of light waves, right? Light, reflection of light waves. Light waves. You know, we've not discussed light waves alone, so we'll now discuss it now. This is the change in direction of light waves. Change in direction of light waves when it strikes an obstacle. This is the change in direction of light waves when it meets an obstacle or strikes an obstacle. This is the change in direction of light wave when it strikes an obstacle. Now let's discuss light wave itself. When it strikes an obstacle or meets an obstacle, anyone you write, an obstacle. When it strikes an obstacle, the next one, obstacle. Now, let's discuss light waves. This is one of the electromagnetic spectrum. Light waves. This is one of the components of the electromagnetic spectrum. This is one of the components, right? Light waves. This is one of the components of electromagnetic spectrum. One of the components of electromagnetic spectrum. Do you understand this thing I explained that time? Okay. This is one of the components of electromagnetic spectrum. It exists between the 400 spectrum. It exists between, just put it as point 2. It exists between 400 nanometer to 700 nanometer of the spectrum. Nanometer wavelength of the spectrum. So this wavelength of light. Exactly. White light exists between 400 nanometer to 700 nanometer. Let me explain. Let me quickly give you this metric system. If you hear micro means times 10 to minus 6. And this way it is written. For example, meter, micrometer. Then we hear milli. Milli means times 10 to the power minus 3. Here, millimeter. Is it clear? We hear nano, which is this. It means times 10 to the power minus 9. Okay. For example, meter and nanometer. We hear the next one is pico. Times 10 to the power minus 12. For now, let's stop here. Picometer. Then, of course, if you want to advance forward, if you hear kilo, yeah, PM, picometer. If you hear kilo, this one is times 10 to the power 3. If you hear mega, this one is what? Times 10 to the power 6. If you hear giga, no. Then tera, times 10 to the power 12. Good. Is it clear? Alright. So now, in your listening, they might want to confuse you. See, this is the same as 4. You know, this is 400 times nano is what? 10 to the power minus 9, right? So by the time you remove these 2 zeros from here, it becomes 4 times 10 to the power minus 7. So 7 times 10 to the power minus. Is it correct? So they are the same. They are saying the same thing. Don't forget it. Point 3. It has the speed of mega, MEGA. The next point. It has the speed of light is what? 3.0. So 3.8 times 10 to the power 8 meters per second. That's the speed of that. White light has the Røyde spectrum. White light has the Røyde spectrum. That's the next point. Have you written the speech? The next one. White light has the Røyde spectrum. The Røyde spectrum. Hence, it is polychromatic. Hence, it is what? Polychromatic. It is polychromatic. chromatic. So when we are dealing with color spectrum, we deal more with this. Is it correct? Now, body spectrum. Hence, it is polychromatic. You have to be fast, please. So don't forget, how is this light wave formed? Because it's part of the EM wave. It is formed when the electric field of the earth and the magnetic field of the earth, when they interfere, exactly when they are traveling at 90 degrees to each other, that is when light wave is formed. So this light we are seeing, that's what's happening. Is it clear? Alright. Now let's go to um I've talked about properties of light, right? Alright. Ray. Yes. This is the path. Polychromatic on the bottom. Let's talk about ray. Polychromatic. Now let's talk about the ray. This is the path. This is the path taken by a packet of light. Packet of light. In brackets. Photon. By a packet of light. The path, PATH, taken by a packet of light. See, the reason why I use packet of light, not say photon immediately, is because when we get to this, we'll start talking about photons in photoelectric effect, quantum mechanics and all. Photon is, you see this light you are seeing, they later discovered that it travels in small packets. You know, like, think of it as a drop of water, and this light too is like that. Small path. So the path through which it takes is the path that we used to see. Is it clear? So that path that it takes, that road that it passes through, is the ray of the light. Is it clear? On your touch. Turn on your touch. Does it not touch? God bless you. Okay, it's done. Now I want you to notice something. If you are using a glass, you will notice that this thing scattered somehow. And it's called diffraction. I will explain that later. My glass is not recommended, but try to look through it. Try to look through it. You see that it's scattered. As if it's scattered. So you see those single lines there. That one line there. What you are seeing, what you are actually seeing, that plenty, is called a beam. It's called what? So this is a beam that we're able to see. But we can isolate it into one. It's called a ray. It's called what? Alright. So a ray is the path taken by a photon of light. Is that clear? Many rays make a beam. 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 Type of rays, one. Type of rays, one. Incident ray. Yeah. Incident ray. Two. Reflect. Now, wait. You don't need, let's just list it. I'll tell you what they are. You don't need to write note on it. Incident ray. Let's just list them. Reflected ray, refracted ray, and emergent ray. Now, when we are dealing with reflection, we only need two. We need this incident and reflected. When we deal with refraction, we need incident refracted, and emergent. Is it clear? Now watch. When we have a surface like this, a solid surface, like let's turn on that thing again. So this ray cannot go beyond this. Is that clear? This is a solid body. In the case where we'll be dealing with reflection, we'll be dealing with mirrors. So a mirror, in your mirror at home, what's a mirror? It's just a glass that is coated on one side with silver. Do you understand? That's how to make mirror. You can use this aluminum foil too. Put aluminum foil at the back. You see that your glass will become mirror-like. Do you understand? Okay. Now see, it is coated on one side, okay, with silver, and so light cannot penetrate. Is it clear? Don't forget that. Oh. Now I'm picking one ray out of that plenty beam that thing gave me. I'm picking just one line that the photon of light passed. So once it touched here, what will it do? It will bounce off. Now listen, when it bounces, this ray that is coming here is called the incident ray. This ray is called what? Incident ray. Then it's not incidence ray. Incident ray. Say incident ray. Then the ray that goes off is the reflected ray. Now watch. What you'll be asked is now about angle. Now, how do we know the angle at which it will go? Snell found out, a certain man called Snell in the 15th century or 16th century, found out that if you draw a line, if you can draw a line, an imaginary line, that line will be called the normal. Because what? The normal. So if you can draw an imaginary line along the path where that line touches, that the angle of reflection, this angle of reflection will be equal to the angle of incidence. Not angle of incident, it's called incidence. Angle of incidence. The angle of, now first, again, how do you read it? You read it with respect to the normal, not with respect to the surface. This angle here is called angle of glance. This one is called angle of what? Glance. But this one is called angle of incidence. This one is angle of reflection. Is it clear? So Snell found out that the angle of incidence is equal to the angle of reflection. Is it clear? So if I say a ray of light strikes blah 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 and made an angle of 40 granite to the horizontal, what is the angle of reflection? The angle you are given is this. That the ray of light makes, listen, stop writing. The ray of light makes 40 degrees to the horizontal. The angle of incidence makes 40 degrees to the horizontal. That's the angle of glance, right? So what is now the angle of reflection? 50 granite. Because this place is 90 granite. So this place will be 50. And this place will be equal to this place. This is also 50. Is it clear? Is it hard? Very simple, right? Right. There's something I wanted to say. Now, we now understand what reflection is. And I'm talking about angle of incidence, angle of reflection. So that's reflection. It touches here, bounces off. In real life, what I'm showing you is there's a touch. See, a touch. No, I want to show you what's coming out. See, ray of light comes out, right? Many rays. What's many rays called? Beam. God bless you. So this one, when it touches it, bounces off like this. This one. Do you understand now? So we are analyzing only one of that plenty rays. Is it clear? All right. Good. Now let's go to. So you now understand this. Now, understand? So now, right. Properties of light. 1. Light travels in a straight line. Yes. The phenomenon is called rectilinear propagation of light. The phenomenon is called light travels in a straight line, semicolon. The phenomenon is called rectilinear propagation of light. Rectilinear propagation of light. Rectilinear, rectilinear propagation of light. Of light. All right. So we are going to continue later. Is that clear? Let's go to the next class.